Hello and welcome to this week's YouTube video. This video is going to cover recursive algorithms to compute numerical values, implement recursive data structures, and using recursive data structures to store and search for data. So get started in the usual way by creating a new Java project in your lab workspace. Call it week 11. And we're going to get right down to exercise 4, which asks you to write a recursive method to compute Ackermann's function. And Ackermann's function is defined by the following equation. Now, the input is two values x and y, and the Ackermann's function a is defined by cases mathematically. If you're not don't know about this mathematical notation, this is a sign that means by cases. So in the first case, if x is equal to 0, then return y plus 1. If y is equal to 0, then return the result of Ackermann's function on x minus 1 and 1. And for other values, return the result of Ackermann's function on x minus 1 and Ackermann's function on x y minus 1. So let's find out how we can implement this in Java. Go to Eclipse and create a new class called Ackermann's function. Create a main method. So maybe a public static. And we're going to use long to store extra digits rather than an integer. So we'll call it Ackermann's with a lowercase a, and the input is going to be some values x, some values y, and the result for now is just going to be 0, just so that we can get it to work. Out.println, and then Ackermann's, and let's see if we can compute it for the values 1, 1. So how do we then implement this? Let's look at it case by case. The base case is when x is equal to 0, we just return y plus 1. So that's quite easy. If y is equal to 0, x is equal to 0, then return y plus 1. That's the first case, and that is the base case. It's the simplest input that we can provide for this function, and it returns just the result y plus 1. The next case is if y is equal to 0, we return the result of Ackermann's function on x minus 1 and 1. So let's try that. If y is equal to 0, then return Ackermann's function on x minus 1 and 1. Like that. For all other input, we return the result of Ackermann's function on x minus 1 and the result obtained from Ackermann's function on x comma y minus 1. So that's the most complicated case, but really it's not too bad. So let's just replace this return 0 with Ackermann's x minus 1 and Ackermann's x y minus 1, like that. So we can start trying to compute it for certain values, and the lab suggests that we compute it for 1 and 1 1 2 2 3 3. So let's try it for 1 1 and see what we get. Let's just run this as a new. We get the output of 3. So let's step through that. 5. So the input is 1 1, and since that y is equal to 0, we skip that and we go to this recursive step. And then since x is not equal to 0, it skips that. Y is equal to 0, it returns this result. Finally, it returns a result here, and it continues on. Now, if you're a bit confused by these recursive steps, don't be. It's notoriously difficult to follow these, and as a matter of fact, Ackermann's function is a particularly nasty function because it grows very, very quickly. So let's try computing it for values like 2 and 2. See what happens. We get the value 7, 3, 3, 61. But if we try to compute it for the value 4, 4, something nasty might happen. Let's try running that and we'll find out. So I'm running it right now and I get a stack overflow error. And as it turns out, Ackermann's function grows so quickly that the Java stack can't actually contain all the recursive calls. So you can try running it for a bunch of different values, but you'll find out very quickly that this thing grows quite out of control. So we can try step through some of it, and you'll see what happens. You can just try stepping through, and the amount of recursive calls is just far too difficult to follow. Don't expect that you'll be able to follow that, and in fact it just continues for so long that eventually Java runs out of memory and it makes it difficult to compute. So this is an example of a recursive function that is rather difficult, although we can write it very simply. These are the recursive steps here, recursive step 1 and recursive step 2. That's all for this week's lab. Hope to see you in the labs later this week. Thank you very much. Goodbye.